Okay, so hello everyone. This is this first experiment of me recording exercises. So let's just try. Today I'll show you just a few introductory exercises on matrices and linear systems using the Gauss elimination algorithm. So let's just start. Here you have this first exercise. You have to consider these two matrices. This one is 3 rows and 2 columns, whereas this is 3 columns and 2 rows, and this is this is again 3 columns and 2 rows. And the exercise asks you to do some matrix products and compare them. So let's just do it, so that we just recall how to multiply matrices. So first, and also how to sum matrices. So first, what is it? What is B? Oh, sorry. What is B plus C? Well, you just add terms. So it's 3 plus 1, and so on. So this is 4. This is then 7 plus 0. So again 7, and so on. So 5, and here 5. Here 5 again, and here 3. Okay. Oh well. So what about then A times, what about B plus C times A? Well, let's do this. So what do we have to do here? Have to take this matrix 4, 7, 5, 5, 5, 3 and multiply with this other 0, 1, 2, 1, 3, 2. Okay, so you know how to multiply matrices. You take every row with every column, and then you do like 4 times 0 plus 7, 4 times 0 plus 7 times 2 plus 5 times 3. So let's do this. And this is for the first entry here. So let me just check that the sum is correct. So again, 3 plus 1 is 4. Oh, that's okay. 7 plus 0 is 7. 0 plus 5 is 5. 5 plus 0 is 5. 4 plus 1 is 5. 1 plus 2 is 3. That's okay. Just double checking. So what is this here? 4 times 0, 0, plus 7 times 2, 14, plus 15. So what do we have here? 14 plus 15, which is 29. So this is it. And for the second entry here, let's do this other multiplication here with this column, this row, and this column, this row, and this column. So what is this? So it's 4 plus 4 it's 4 plus 7 plus 10. Okay, 4 plus 7 plus 10. So it's 10 plus 11, so it's 21. Let's do the other row. So this row with this column. Okay, so 5 times 0 is 0. 5 times 2 is 10. Plus 3 times 3, which is 9. So here we have, if I'm not mistaken, this is 19. Okay, and the last one, this times this. So we have 5 times 1, which is 5, plus 5 times 1, which is 5, plus 5 times 2, which is 10. So 10 plus 10, which is then 20. Okay, so we have it. And then let's do the other products. So I ask you to do this, BA plus CA, but first, of course, we have to do B times A and C times A. So what about this? Then B times A, so let's just copy. Yeah, sorry. Let's just copy B, 370 and 541. It's okay. Times A, which is then this one, 0, 1, etc. 0, 1, 2, 1, 3, 2. That's okay. That's good. So we do the same thing again. So now what we get here is, I'm just going a little bit faster, hoping not to do many mistakes. So 3 times 0, 0, we have a 14 here. Okay. And then here, 5 times 0 plus 8 plus 3, so it should be 11 here. Sorry. And yes. And here you have 5 times 0 plus 8 plus 3 again. No, sorry. Have to do this. Have to do this times this. So it's 3 plus 7 plus nothing. It's 10. And the last one, 5 times 1 plus 4 times 1, which is 9, plus 2, which is again 11. And now let's compute CA. Okay, so again, C, which is 105, 012, 105, 012. Okay. Okay, and A is then the same one. 012132. Well, okay. Okay, let's do this. So what we have here, nothing. So this first thing. So you have nothing plus 15. And let's do this one. Sorry, this one. So 1, nothing, and then 10. There's an error here. No, sorry. Yes, there's definitely an error by myself. I said 1, this is 1 plus nothing plus 10, so it's 11. Okay. And then this is 0 times 0, this one. This is, okay, 0 times 0, which is 0, plus 1 times 2, which is 2, plus 6, which is okay, 2 plus 6 is then 8. That's okay. And the last one, 0 times 1 plus 1 times 1 plus 4, which should be 5, right? There's probably something wrong up there. Okay, this is so. I think this is it. This times this. Okay, 0 times 1, 1 times 1. this is correct. So there's an error here probably. If you add up here, like now, then you add up this, and it's 29, it's correct. You add up this and you get 21, which is again correct. You add up this and this, which is 19, which is correct. But then here, what we expect is that these two things agree. So we have an error here, and yes, it's very common. It's a very common thing to happen when you do like this kind of computations. But I think the viewers have already spotted it. But now I'm going to spot it myself, and so it's probably around here. It's 5 times 1. What's the problem? Oh, perhaps it's here. Yeah, it's definitely here. So here it's 5. 5 times 1, which is 5, plus 5 times 1, which is again 5, plus 6, which is not 20. Why did I write 20? It's 16. Sorry. Now you see that conclude that indeed B plus C times A is equal to BA plus CA. And this holds in general. Let me write this in nice color. This holds in general. And you can check it. And I think it's easier to check it with letters than with real numbers. But yeah, perhaps we can see it another time in general, or I mean with examples with some letters around. Okay, and that was the first one. So let's go on. Okay, this is nice. So I ask you to find matrices AB such that they don't commute. So A times B is not B times A. But also I ask you to find CD such that they commute. So CD is equal to DC. And yes, let's first do the last one. Let's first do the last one. So there are very easy examples you can make here. I'll show you some. For example, if you take I didn't specify the dimensions, but let's find 2 times 2 matrices just to keep it simple. So as for C and D, it's very easy actually. So if you take, for example, C to be this one, so just zeros, and D to be again just zeros, then it's obvious. CD is again equal to DC, and it's the same thing. But even if you want them to be, different, you can just take C, for example, to be the identity matrix, which is very important, very famous one, and D to be, I don't know, any matrix can do, but let's stick to this one. And again, CD is equal to DC is equal to. But as I said, here, if I take C, the identity, and D, any, so, I don't know, your choice. You put any numbers here, the one you want. Then, of course, you can check that CD is equal to DC and is again equal to D. So they commute. But in fact, it's easier. I mean, in nature, you won't easily find matrices which commute. So I mean, in general, in nature, what you expect is that given two matrices, they don't commute. And it's very easy to find, actually, just by by like direct attempts to find matrices which do not commute. So as an example, for example, you can take A. So let's take this, and then B. Let's take this. So let's do again A times B. So what is A times B? It's this thing. Okay, so let's do the product. So you get 0, 0. Again, 0, 0, 0 here. 0, this is 1 here. And here it's 0. Okay, that's correct. Okay, this is AB and this is BA. As for BA, so let's do this. Okay, let's see. So this is this is 0. The other 1 times 0 plus 0 times 1, again 0. This is 1 times 0, 0 times 0. This is 1 times 0, 0 times 1. This is 0. So you see, they are different. And I mean, in general, as I said, you won't expect matrices to commute. And if you want an explanation of this, we're going to view matrices as a way of representing, like, let's say, processes. And you know, I mean, kind of processes are not in general commutative. Let's think about it. Just think. You are like, you want I don't know, for example, you let me just think a bit about it. You can make very nice real life examples to convince yourself that most processes do not commute with each other. So typical one, I think, for example, let's say you want to put on your shoes, and normally what you do is you put on your shoe, and then you tie the bows. But I mean, this is the normal way to do this. But if you tie the bows before you put on the shoe, then it's kind of different. You can see it, and I think you can make some more examples yourself if you want. But okay, if you want as a let's say homework, find more examples of non-commuting matrices. Just think about it, and also, if you want, of commuting also. Just to make you like a little bit more accustomed to this language. Okay, that was the other one. Okay, so now let's start doing linear systems. So, you know, I think from high school, or I don't know, linear system, what does it mean? To solve a linear system, you have few equations with a few variables. You can have many equations with many variables, and it can be a different it can be, for example, 3 equations and 2 variables, or 2 equations and 3 variables, or as in this case, 2 equations and 2 variables, and they are linear. What does this mean? They are linear. It means that the variables compare just they're not, they just compare by themselves, and they're not, you can't find things like x squared, y squared, x times y. So the degree of the variables is always 1. So this is not allowed, and this makes things more easier. This makes things easier because you know from the theory, you learn to know from the theory that any linear system can be represented by an equation involving matrices, vectors, and vectors. And with this kind of new way of viewing linear systems, then you can find more interesting and straightforward, if you can say that, ways of solving this kind of systems. Let's see. So you have this, and normally what you could do is just like manipulate it. So find, for example, x from here, and you get x is equal to 3 plus 2y, and then substitute x in the other equation below, and this means that you have 3 plus y minus y is equal to 9. Okay, and then you just go on solving things. So it's 6 plus 4y minus y, this is a 9. Yes, is equal to 9. So this means that 3y is equal to 3, I hope. So in the end, y is equal to 1, and then you substitute again here, back, and you should find then x is equal to 5. Let me check. Yes, it should be correct. So I mean, this is a way of solving systems, linear systems. You can, in principle, you can always employ this. You manipulate things. I mean, a system means that both equations have to be true at the same time. So you can use one or the other to find things and substitute and so on. And this is a very basic way of solving systems. But but this is a linear algebra course, so we are going to solve linear systems in a different way, using the language of matrices and the famous Gauss-Jordan elimination, which has the advantage that it's an algorithm, so it's something you can instruct computers to do, and this is probably important to you as Informatica students. So what do you do here? What you do is as follows. So you introduce a matrix, which is the coefficient matrix, and in this case it's going to be 1 minus 2 minus 1. Okay, you introduce a vector, which is just the variables you want to find, and then you introduce this, let me call this x with an arrow there, and you introduce the vector of the known values, if you want, 3, 9, and then what you know from the theory is that solving this is the same as solving this equation, which now involves matrices and vectors. But to do this, you can use the famous Jordan elimination, Gauss-Jordan elimination. So How do you do this? The technique is as follows. I mean, I think it's easier to use it by examples than to show it in theory, because I mean every time I try to recall it in theory, I personally fail, but as I do some example, then it's kind of natural, and it's like very mechanical. So the idea is as follows. You write your system as follows. So 1 minus 2, 2 minus 1, this is your A, and then you put your, oh, this is a very bad 9, this is nicer. So, and you put your B vector here, and now you have some allowed line operations you can do. So, first operation you can do is multiply the second line by, for example, minus 1 over 2. What happens if you do this? The first one is the same, whereas this one now has minus 1 over 2, minus 9 over 2. Let me see. Just check it. Okay. And now another allowed operation you can do is you can sum. Let me call this the first and this the second. So you can replace the second. Now replace the second with the second plus the first, and keep the first. So what happens? I've multiplied the second by minus 1 over 2, so that I get a 0 as follows. So the first one is the same, and the second one is replaced with the sum of the two lines. So it's here you get a 0, and here you get minus let me see. Yes, should be. Yeah, it's correct. Yes, sorry. Minus 3 over 2, I think. And here, what you get here, it's 3 plus this thing. Okay. So 3 is, you can view it as 6 over 2 minus 9 over 2, which is again minus 3 over 2. These are just computations, huh? Okay, so now here you can multiply this by just minus 2 times 3. So what you get is just 1 minus 2. Oh, sorry. 1 minus 2, 3 here, 0, and this is a 1 here, and a 1 again here. And now it's and now you get the system in the so-called row echelon form, where you have this triangular. It's this triangular form with the leading ones, and this is nice. And now you can switch back, since now it's very easy to go on. I think you can normally switch back to variables. So now what you get is that y is equal to 1, and that x minus 2y is equal to 3. But now it's very easy to substitute. So you get x minus 2 is equal to 3, y is equal to 1, and so x is equal to 5 and y is equal to 1, which is the same as we found before, right? I cancel, but it should be correct. Okay, very good. Okay, so in general, you can do this like Gauss-Jordan elimination until you get something which is like triangular, like this, and then when you have this, it's normally very easy to go to find the solutions. There is something we have to say, and it comes with the following examples, namely, it doesn't necessarily happen that a linear system has a solution, or even if it has a solution, it doesn't necessarily means that this solution is unique, and this is very important. So let's see this other example here, and let's just do the Gauss elimination. So this thing 5 minus 4 6 and then 8. Okay, so what we can do here, just multiply the second by 1/2, just divide by 2 if you want, so that you get 2 minus 3 5, and this is now minus 2 3 4. Okay, and now you can do as before. The first you keep, and you replace this, the second one, with the sum of the second and the first, and this is an allowed operation, as you know. So you get 2 minus 3 and the 5 here, and then you get something strange now, namely this is a 0. This is a 0. You make the sum, just the sum. This is the second, sorry. You make the sum. You get 0 0 and a 9 here. And now we have a problem, because now if you substitute variables again, you get 2 times x minus 3y equal to 5, but then here it's 0 times x plus 0 times y equal to 9. But from this you get 0, which is equal to 9, and this is a contradiction. This symbol sometimes means contradiction. So what does this mean? It means that, well, I'm trying to find a solution, but whenever I try to find a solution, I get instead a contradiction. So the meaning here is that the system has no solutions. Or if you want to use a slightly more formal notation, if you denote by S the set of solution of, let's say, this, solutions of this, then what we've said is that this set is the empty set. The empty set is the set which does not have any element. Okay. Whereas, I mean, if you want here to use this notation, you can write S as just this set with just this one element. So this means the solutions written in this vector form here. And this is what you normally do. You write, you think of a linear system as a system involving vectors like this, and then you write solutions as vectors. So this means that this is x and this is y, of course. Okay, so this one has no solutions. And let's go on and let's do this. Sorry, which is slightly more difficult. I mean, computation-wise at least. So let's hope I don't make mistakes here. So let's do this, and it's the last one we do actually. So let's write it in matrix form. So this is again 1 1 1 1 1 3 3 4 2 4. That's okay. Okay, this is it. Okay, so let's multiply rows in a way so that we can eliminate, we can put some zeros here and here. So what are we going to do is multiply, oh, sorry, wrong color. So multiply the second one by -2. So the first one you keep it. And the second one is -2. And this one is -2/3. Okay. So this is what you do. And what you get here is -2, -2, -2, -6. And here it's -2, -8/3, -4/3, and this. Okay, let's go on. Now, what you do, of course, is then the first you keep, and this you replace it by the sum with the first, and again here you sum you add the first one. So what you get here, sorry, just graphically, okay. Yes, graphically it can be difficult. Okay, very well. So the first one you keep. As for the second you add. So this is 0, this is 0. That we know for sure. As for the other ones, just be careful. This is 1, this is -1, and this is -5. Okay. This is 1/3. And this is -1/3, and this is -5/3. Okay, that's good. That's good. That's good. That's very good. Okay, now for the sake of like not having fractions, just let me multiply this thing, this row, by 3 again, and then what we get is then this. So okay, 2, 3, 1, again 1. This is the same. As you see, at every step we are careful to do operations we are allowed to do. This is very important. 1 minus 1 minus 5. Okay, let me multiply by -1 this row again. So let me just change the sign all around. So here, this is -1 plus 1, this is plus 5. Okay, sorry. Okay, now it's kind of nice, right? Because we can try to sum. This you keep, but this you substitute it with the third plus the second. What you get is as follows. So here you don't do anything, -5. But here is something interesting happens. If you add up these two things, then you get 0, 0, 0, and another 0. So what does this mean? This is important. This is sorry, doesn't matter. Okay, this is very important Why? It says when you get something like this, so 0, 0, 0, and then another 0, this means that actually one of the equations is actually redundant. So there is some redundancy in the system. And now if you substitute back the variables and you go on, look at this. This is not really row echelon form. You don't have a 1 here, but I mean, you have a 2. It's not a big problem. It's, if you want a 1 here, then you get some fractions, and we don't really like fractions, so okay. So you get this. This is 0 equal to 0, and I mean, this is true. This is like kind of a void condition. This is always verified. Of course, if here we had something different from 0, then we would have known that the system had no solutions. But in that case, it's different. So we just go on, and I mean, this is redundant. We don't even have to write it again, anymore. Y minus z equal minus 5, and then you can. What happens here is that you can't find just one solution, because, for example, from this one, you find that y is minus 5 plus z, okay, and then you can substitute here, namely 2x plus. Let me just do the computations. Minus 15 plus 3z plus this is equal to 1. Okay, and you go on, and what happens? Just take this y minus 5 plus this one. Okay. And here, let me just rearrange things. This is 2x equal 16. Wait. Okay. Yes, 16 minus 4z, okay, which means that x, x, which is now 8 plus 2z, and y, which is minus 5 plus z. I mean, but you can't, you know this, but z can vary. So if you take any of this z, it can be any number, and then if you substitute this x and this y, you will get solutions, and these are all of them. So what you normally do is you write something like this. You think of z as a parameter equal to t, and then you can write the solutions. You can write it in this form if you want, as a vector. This is it. So you have something and something which is multiplied by t. Sorry, there is an error here. This is minus 2 z. Okay, so this is minus 2. Let me just substitute this. T. Okay, this is minus 2. Sorry, just wait a minute. Okay, this is better. This is minus 2. This is 1, and then 1, and then 1. So the general solution is described as this in this way. If you want to write them down a little more formally and write, like, for example, S, again, solutions this system, then you would write something like this. You can write something like this. This is a perfectly rigorous way of writing things. Did I? Wait a minute. Well, I hope it's correct. They should be. No, there's an error. Sorry, I copied. My bad. Here. Okay, that's good. That's good. That's very good. It's okay. Okay. So this is a perfectly rigorous way of writing solutions, like here. So you get you get an infinite set of solutions, but they depend just on one parameter. Then this is the parameter. So if you want, this is like a fixed starting value, and then they describe this like infinite set with just one parameter. It can happen that you have more than one parameter, but yeah, we'll see it. We'll encounter more examples later. Okay, and to finish, just a final exercise, which is slightly more different. Now we have a family of systems which depend on a parameter. So I ask you, determine for which parameter lambda in real numbers this following system has at least one solution. And this is it. This is kind of different, but let's try to approach it with the Gauss elimination as we know. So let's try. So what we do here? Sorry. Sorry. Okay, let's just start. So it's 1, 2, minus 3, and this is lambda. To start, we keep it. We don't put restrictions. Okay. And this is 2 lambda, and this is 1. Okay. Okay, so now let me just multiply, for example, this by 1/3 minus 1/3, and this by 1/3, so that you get this. Okay, minus 1, minus 5/3, plus 1. Okay, minus 1, minus 4/3, minus 1, and 1/3. Okay. Okay. Now you can replace this row with this plus this, and this row with this plus this. So you do as before, as we've seen before, 2 plus 1 and 3 plus 1 again. So you get 1, and so 0, 0, which is good. And then if you do the computations here, you get 2, 1/3, 2/3, minus 3, minus 2, minus 4. Okay. And here, just be careful. This is okay, this is 1/3 lambda, and this is lambda plus 1/3. Okay. Okay. Now let's multiply the rows so that I get rid of the fractions, just for more clarity. So you get this, lambda 0, 1, minus 6, 0, and this is true. I'm multiplying by 3. just to get rid of the fractions. So this is lambda, this is 3 lambda plus 1. Okay, very good. Now let me do this operation. You keep the first, you keep the second, but as for the third, you replace it with the third minus 2 times the second. Okay. Let me do this again, perhaps here below. Okay. So you keep it, this one, this one, this one, and this is lambda. Okay. And but when you do this, what you get here, this is the same, of course. Now, be careful, it's the third minus 2 times the second. So this is, if you see, if this is 0, 0, 0, and lambda plus 1. So this is an interesting situation where you see here, so if, as before, if this, let's be very careful here. This is the key part. So if lambda plus 1 is equal to 0, then you get something like, so this means lambda equal minus 1, by the way. So you get something like this. This is minus 1, and this is 0, 0, 0, 0. So okay, this is redundant. This row is redundant as the example before. But you can go on. But if, let me just erase here. If this, the other case, if it's different, then the third row, row 3, is 0 equal to lambda plus 1, which is different from 0, contradiction. So if you want, if you hope, if you hope to have solutions, you need lambda equal to minus 1. And okay, as an exercise, then find the solutions in this case. Okay, and that's all for this first experimental recording, which I readily make you available. And okay, and then see you next time, and let's hope that technically it's everything okay.